So finally, here is part 4 of the review for the finals, and this is on the chapter of thermodynamics. Now, this is a completely focused review, which means that if you understand what I speak of here and prepare everything surrounding these topics, then you're good. So first of all, let's look at the first law of thermodynamics. According to the first law of thermodynamics, if you have a system and if you have heat entering the system, then that heat is going to be used in two ways. Number one, a part of the heat is used to increase the internal energy of the system. And number two, a part of the work is going to be used to do work. So as shown in this diagram, you have a cylinder fitted with a piston which is movable, and delta Q is the amount of heat entering the system, and the system is a gas here in the space between the piston and the cylinder. So when delta Q amount of heat enters, since the piston is free to move, it will be pushed out from the original position A to the final position B, which means there is a change in volume. So the change in volume is delta V. And also the temperature of the gas increases, and that is reflected in the change in internal energy. Now, change in internal energy is connected to the change in temperature. So delta Q is the amount of heat entering, out of which delta U is the quantity of energy used to increase the internal energy, and then there is another part used to do work. According to the first law of thermodynamics, the change in internal energy is the difference between the heat entering the system and the work done by the system. You got to be careful here because I said heat entering the system. Now, heat entering the system is taken as positive, while heat leaving the system is taken as negative, naturally. Again, work done by the system is taken as positive, which means a positive with a negative will leave this as a negative. But work done on the system, this part becomes negative. So a negative multiplied by negative will make this positive. So keep that in mind. So as an example, if delta Q is 600 joules and the work done by the system is 200 joules, delta Q here is the heat entering, so that's plus 600 joules, and delta W is the work done by the system, which is again positive 200 joules. So when you substitute into this equation, you're going to get positive 600 minus positive 200. So that's 600 minus 200, which is 400 joules. Now, let's say that the amount of heat entering was 600 joules, but work done on the system is 200 joules. What would be the change in internal energy now? Now the change in internal energy would be 800 joules. 600 minus 200 joules. So that is what if work done on the system is 200 joules, then you got to take it as negative 200. And then the change in internal energy is 800 joules. All right, let's now move on to the second law of thermodynamics. I am presenting the second law of thermodynamics in the simplest form possible, which is if you put a hot object in contact with a cold object, a hot in contact with the cold, then heat naturally flows from the hot to the cold. We don't have to do anything, it's spontaneous. So that is the simplest statement for the second law of thermodynamics, that heat naturally flows from hot to cold. So what about if you want to make heat flow from cold to hot? That is not natural, that is not spontaneous, and therefore we have to do work on the system. That is exactly what happens in a refrigerator. So to make heat or to transfer heat from a cold to a hot object, we have to do work on the system. That is, in a sense, the second law of thermodynamics. To move heat from cold to hot, work has to be done. But there's another facet to this. We're going to connect this with entropy. Entropy is a measure of disorder of a system. So the more disordered a system is, the greater its entropy. So if heat enters a system, so heat, let's say, enters a gas, what happens to the molecules? They start moving faster and it becomes more random. The motion becomes faster and more random. That means when heat enters a system, its entropy increases. When heat leaves a system, its entropy decreases, right? Okay. Next up, we have to look at the heat engine. What is the heat engine? It is a device that converts thermal energy into mechanical energy. A device that converts thermal energy into mechanical energy. The blueprint for a heat engine was given by a French engineer called Carnot. So what I'm drawing here is Carnot's engine. In Carnot's engine, you have a hot source, which is at temperature TH. This is a place from where heat can be absorbed, so that's why it's hot. It's called the source. And then there is a cooler or colder object at temperature Tc, C for cold, to which any amount of heat can be rejected. Any amount of heat can be thrown out. That's why it's called the sink, to throw the waste. So you have the source from where you can get any amount of heat, and you have the sink to which you can throw the remaining heat. But then you also have the substance that can take the heat from the source, utilize a part of it to do work, and then reject the remaining heat to the sink. So again, that's the working of the heat engine. So let's say that QH is the heat taken from the hot source, W is the work done, and QC is the heat rejected to the sink. So do not be confused between TH and QH. TH is the temperature of the source, while QH is the amount of heat in joules taken in by the working substance, and QC is the heat rejected to the sink. So what's the relation between QH, QC, and W here? Well, of course, work is the difference between QH and QC. Work is the difference between QH and QC. And the efficiency of Carnot's engine is defined in three ways. Number one, it's work done over QH, which also can be written as QH minus QC by QH, because work is QH minus QC. In terms of temperatures, efficiency is TH minus TC over TH. So we have basically three formulae. Here one, second one, and the third one. And the working of Carnot's engine can be represented by four processes. These are called four strokes. That's why it's called a four-stroke engine. And on the pressure volume diagram, here is the first stroke. That is the isothermal expansion. So when the gas takes in heat from the source, the piston moves outwards and it expands. Followed by the adiabatic expansion. That's the adiabatic expansion. Then the compressions, the isothermal compression followed by the adiabatic compression. So in Carnot cycle, we have two isothermals, AB and CD are the isothermals, while BC and DA are the adiabatics. So we have two isothermals and two adiabatics. If you look at it another way, you have two expansions and two compressions. This AB is an expansion, BC is another expansion, CD is a compression, and so is DA. So that's Carnot cycle. And the useful work done is given by the area of Carnot cycle. That's the work done, which we could also calculate as QH minus QC, remember? So you can get the work either by taking the difference between QH and QC, or you can find the same work by finding the area of the pressure volume diagram. Next up, let's look at a refrigerator. A refrigerator is actually the heat engine working in the reverse order. So it has the source, the sink, and the working substance as before. But if you watch closely, you see that instead of taking heat from the source, heat is now taken from the sink. The working substance takes in heat from the sink. Now that is the engine. I'm going to clear that out. And you will see me changing all the arrows, and I wanted you to see it. That's why I'm doing it this way. Now look at the arrows. QC is the heat taken in from the sink. The arrow is pointing that way. And then you also see the arrow reversed here. That means work is not done by the working substance. Instead, work is done on the working substance. And heat QH is rejected to the source. So although the symbols QH and QC are all the same, you see that it's in the reverse order. Therefore, when we try to define the efficiency of a refrigerator, we do not call it efficiency, we call it the coefficient of performance, because it's going to be more than 100%, and it's defined as QC over work. See, it's flipped, and then you have QC instead of QH. It's flipped. So coefficient of performance of a refrigerator is QC over work. And since work is the difference between QH and QC, you can also represent it that way. And in terms of temperatures, once again, you can write it similarly as TC over TH minus TC. So that is how you write the coefficient of performance of a refrigerator. Now, moving on to entropy, I think I already mentioned that entropy is a measure of disorder of a system, and that when heat enters a system, the disorder increases. That means the entropy also increases. I said that. But here we got to find out how to calculate the change in entropy. We got to do the simplest of simple calculations, but also understand that according to the second law, the disorder of the universe is increasing. That means the entropy of the universe taken as a whole is increasing, and there is no way to avoid that. But to find the change in entropy, we got to do the heat entering or leaving divided by the temperature. So that is the formula. Delta S stands for change in entropy. So S is the symbol for entropy. Delta S is change in entropy. Delta Q is either the heat entering the system or leaving. Remember that if heat is entering the system, means coming into the gas, then the entropy increases. If heat is leaving the system, then the entropy decreases. And T must be in Kelvin, and that is the temperature at which the change is taking place. Now, to show you how you can use this in a problem, Let's consider 200 grams of ice. And let's imagine that the ice is melting at 0 degrees Celsius. What is the change in entropy? Now, in order for ice to melt, it has to get heat. So first we got to find the heat that is required, which is given by mass times latent heat from a previous chapter. Mass times latent heat, and mass must be in kilograms, so that is 0.2 kilogram, times the latent heat of ice will be given, that is 3.36 times 10 to the negative, times 10 to the 5, and the temperature is 0 Celsius, which is 273 Kelvin. So you calculate, you get 246 joule per Kelvin. Joule per Kelvin is the unit of entropy. What about if water was being frozen into ice? Let's assume that it's the same mass of water that you're freezing into ice at 0 degrees Celsius. The difference would be now you have to remove heat from water in order to freeze it. And therefore the change in entropy in that case would be negative 246 joule per Kelvin for the same mass. Let us work out one more example to find the change in entropy. So water, let's say 500 grams of water is heated from 10 Celsius to 80 degrees Celsius. What is the change in entropy? So this is not a change of phase, so this is heating a substance. And in this case, the formula to be used for quantity of heat is MCAT, mass times specific heat times change in temperature. The specific heat of water is given as 4185 joule per kilogram per Kelvin. And so first we find the quantity of heat required, which is mass times specific heat times change in temperature. Mass is 0.5 kilograms. Specific heat is 4185. And the change in temperature, 80 minus 10, that's 70. 70 Celsius. If you take the change in temperature in Kelvin, you know it'll still be the same. The change will be the same. So that is a big number there, 146475 joules. But that's just the quantity of heat. Now you got to divide this by the temperature. What temperature are we going to divide it by? Because it started out at 10 and went to 80. Now we take the average temperature. The average of 10 and 80 is 45. How do you get that? 10 plus 80 divided by 2. And that is in Celsius. So add 273 to 45 and then use that number. So 273 plus 45. That gives 318 Kelvin. And so when you divide, you get 460.6 joule per Kelvin. Is this positive or negative? It is positive because water is being heated. On the other hand, if water was being cooled from 80 to 10, then you would have done the same process, but you would have got a negative. So keep that in mind, and I'm glad I finished this review just in time, in under 20 minutes. Thank you. Hope this helps you. And if it does, at least give it a like and share it so it benefits every other student who takes physics. Thank you all. Wish you the best for tomorrow's final exam.